Okay, welcome to this webinar. My name's Ty Newell, and this webinar is coming to you from the middle of nowhere. I'm in central Illinois, Champaign-Urbana, about 2 hours south of Chicago on a cold, frigid day, about to get colder. And so that's appropriate to our discussion as we look at some ventilation and fresh air, indoor air quality subjects for cold winter days. Thank you for taking the time to join with us in this webinar. And I will hold questions. Please write any questions in, and then I'll work to answer those at the end. I have a little difficulty walking and chewing gum at the same time, and so trying to keep my train of thought is difficult enough as it is. And so we'll try to answer any questions, and anything that I don't get to or don't satisfactorily answer, please contact us at any time on that. So anyway, this is a webinar on smart ventilation and smart air distribution. You may have seen some of our past webinars, for example, on designing net zero energy homes, on effective ductwork design, but things related to building and designing a sustainable, healthy, and energy efficient home. So this is who we are. We're Build Equinox. Ben Newell is my son and my boss. He's the president of Build Equinox, and Alex Long, who is vice president, along with myself. And we're all three mechanical engineers with a background in research and development for a lot of large HVAC companies, refrigeration companies. But then this is a venture that we have developed called Build Equinox to work on sustainable technologies to allow us to live in a sustainable manner. And I'm talking to you from a 100% solar powered business. We are a net positive business. It's not an exotic building. It's a 4,500 square foot Morton building. But where I live and where I work is solar powered, along with the majority of my transportation with 2 electric vehicles. And so this is part of our mission, and we view indoor air quality and maintaining a healthy home as being critical to sustainable living. So the objectives today, 2 simple ones: smart ventilation. I hope to give you, through both analysis as well as field data, a better view of how smart ventilation works, some information about the energy associated with a smart ventilator, such as this serve system that we've developed. And then to talk about smart air distribution, something that kind of gets left as an afterthought, something in which people have not been thinking about enough, and in many cases thinking about in the wrong manner. And so I hope to give you some background into the importance of air distribution, and then the ways it should be done and the ways it should not be done. Among other things, because we work with so many folks throughout the country, throughout North America on residential projects, we often hear someone tell us that the house they're designing or the house they're building or the house they're going to live in, that, well, they don't have much of a need for this or for that. It is extremely important that you think in terms of all those who are going to live in that house many years beyond you, at least 5 generations, if not 10 generations of people beyond your current needs. And so putting advanced thinking together so that you're also making this house an easy one and an effective one for someone in the future to live in. Maybe the house isn't going to be have much occupancy when you move in, but maybe in the future it's going to be packed with people. Maybe it'll be totally different. And so think about that beyond just your current objective. Just a little bit of an overview on smart ventilation. To our thinking, a smart ventilator means that it should know what the air quality is within your home and then ventilate when needed. And with current sensors that we find viable, carbon dioxide and then total volatile organic compound sensors, that these are state-of-the-art technology. Other viable sensors will be coming along, ones that may break down the pollutants to an even finer analysis to its components, formaldehydes, alcohols, other substances that we would like to maybe know more detail about. In addition to monitoring the air quality, also seeing when it's nicer outside than indoors. So for example, in most locations at night, air is less polluted outside than it is during the daytime with car exhaust and activity and solar thermal buoyancy raising up dust into the air from the ground. And so nighttime often is a nice time to fill your house with fresh air. And then oftentimes it's nicer in temperature and humidity than the inside. Those of you who are fortunate enough to live in the Intermountain areas, like the Front Range of Colorado and Salt Lake Valley, you have about 7 months or more out of the year when it's pretty nice outside. Might be during the day or at night, but there's a lot of times when you just simply want to bring the outdoors in, equivalent to automatically opening a window when it's nice, and then closing it when it's not. So a smart ventilator does this. A smart ventilator should be something that has high energy efficiency, and different ways that you may do this. The manner in which we'll be considering for this is through a heat pump, exchanging energy between incoming fresh air and outgoing indoor air, exhaust air, and exchanging energy when it is beneficial to do so. It's important to archive in indoor air quality data. We'll talk about that at the end, but this is how we're going to learn about ourselves on a personal basis and what helps us feel better and what doesn't, and then hopefully what we can do about it. And in a collective manner among data among all of us, that we may start to see trends, things that are good to do, things that are not good to do. A lot of it common sense, but still being able to quantify for any of us in a certain region, a certain stage in life, what makes us feel good. And then finally, even though we are talking about an advance in technology, something that gets complex when you get down to the chip level of designing the controls and the computer algorithms, the goal is to simplify our lives, not to put another level of worry and stress on us, which is very important for reducing for our health, but making it simpler. And you might think in terms of like the upcoming autonomous vehicles. As complex technologically as these may become, for me as an older person, I'm looking forward to it because I think that means I can get quite old and still be able to move around and see friends and interact socially with other people and not have the worry about driving, not have the worry of managing a vehicle. So we view the technology behind this in that manner. Smart air distribution coupled with smart ventilation. So smart ventilation, as we look at it, is managing your house as a whole and determining when it needs to have fresh air. But then you need to distribute it. And you need to distribute it where it's needed and when it's needed. And the house is a very dynamic situation. In fact, much more dynamic than a typical business. We monitor, do field studies of both. Typical business, people show up at 8, they leave at 5, they might go out at noon, but it just kind of increases in indoor air pollutants and then decreases at the end of the day. Your house is a hotel, it's a restaurant, it's an entertainment zone, it's a school, it's all of these things, and people are coming and going at unknown times. They're showering, they're cleaning, they're cooking. It is a very, very complex environment, and it's essential that a ventilation system can move with the dynamics of the house. And with a effective distribution system, it maintains a high quality throughout the entire house. Your bathroom should have just as good of air quality as your living room, as a bedroom, and as a kitchen. And it's important to efficiently use all the fresh air that you've brought into a home. In too many systems that are simply either exhaust only or supply only, or what we call one and done, but so-called balanced ventilation, but a constant flow type ventilation system, 75–80% of the air brought into the house may never see a human. It may just move through the house, and it hasn't done you any good by keeping your air fresh. And so as we look at some of the ventilation results, you don't want to be deceived into thinking that just because on average the house has good air quality, locally where you are, if fresh air isn't delivered there properly, it could be very, very poor. We feel recirculation of air throughout a house is essential. Recirculation is a very simple tool, a very simple way to distribute fresh air that's been stored in the unoccupied zones. Recirculation is a way to get indoor particulates to filters and to keep the particulate concentration at an acceptable manner. And it is a myth that a highly sealed home has no dust. In fact, 90% or more of the dust, and you will have dust in a highly sealed, high performance home, you are the source of it. You're going to shed a pound of skin a year. Every time you move your arms and legs, you're abrading textile particles off of your clothing. There's dirt and dust coming in every time you open and close the door. You will have dust and every time you cook, and you need to get these particulates out of the air. And recirculation is the effective means for doing that. And then recirculation improves comfort. It moves warmer air from one part of the house to a cooler part, whether you're trying to warm or cool, but it helps on the comfort side. And then when a home gets more complex, typically when it gets larger relative to its occupancy, then you may start thinking about additionally spreading sensors as well as using zone control to more actively move air where it's needed and to remove air from where it's not. So here's a picture of all the bells and whistles that one might have. This is our new Serve 2 unit, and this is not an advertisement for the Serve 2, although you'll see me referring to some of the data we've collected. Later in February, Ben is going to have a webinar that talks specifically about the Serve 2 with the sensors and features. But the basic Serve unit itself, for most homes, it's doing the recirculation, it's doing all the sensing of air quality, as well as contributing its excess capacity toward heating and cooling and dehumidification to a home. And then as you get larger, this array of sensors, the wireless sensors, we use a wireless protocol that is a battery-free sensor, and you can see small solar PV panels that power these sensors, recording and reporting carbon dioxide, temperature, relative humidity back to the serve unit, and then an array of dampers that this is actually for a home that has 5 zones spread throughout it. That these dampers open and close as needed for moving fresh air where it needs to be emphasized. So let's just start off and just state smart ventilation, when it's done properly, it works. Here's data from 34 homes, but these smart ventilation units are now in a few hundred homes. And so in some sense, because of our system's online monitoring capability, we're running what I think is perhaps the world's largest indoor air quality experiment that's ever been conducted. But here's 34 homes from in Vermont from about a year ago, January through May, when the homes typically would be sealed, and the average CO2 and VOCs. The bottom axis is the set point that the homeowners used. By and large, most of these homes were set at 1,000 ppm whenever VOCs or CO2 would go above 1,000 ppm. Then the serve would kick on and bring in fresh air. You can see one home where that person was particularly sensitive to the air quality level, and they set it at 600. Now, 600 parts per million requires a lot of fresh air, but you can see that it managed it. My house, which you can see online from our buildequinox.com site, you can see under the Take Control section, live data from our house, and then also archived. You can see over 4 years of data since we added the online monitoring capability to the serves. So you can see that in detail over a long period of time. Now the blue dots, which are the VOCs, you can see that in all electric homes, which these 34 homes are, that VOCs tend to dominate over carbon dioxide. Not always, but when they do, that indicates that that there's something else going on in addition to the VOCs that a human puts out. And when VOCs are similar or somewhat less than the human CO2 output, then that's telling you it's basically human VOCs that are being sensed. I'll mention that the VOC scale on this is one that's correlated to the human's CO2 output. And so they're not the true VOC scale. There's a conversion over to the parts per billion for the soup of chemicals that make up VOCs. But this gives you some perspective as far as whether the VOC output is human-like or human level or greater than that. And then just a little perspective on energy, because a lot of folks focus on energy and we feel to the detriment of their health. And it's important to think beyond energy and start putting your health into perspective. For a 20-degree average outside temperature, here's data, the shotgun blast of 13 identical homes with very non-identical people living in them. This is 2 years worth of energy data, hourly data that then has been put into daily terms over a 2-year period. And you can see that some homes at 20 degrees were maybe using 20 kilowatt hours per day, about $2 to $3 worth of energy. And then some other homes in this area were using maybe 40 to 50, some as much as 60 kilowatt hours. Now that's quite a bit of difference for an identical home. They had different occupancies, and these yellow dots are computer simulation of a 1-person occupancy and a 3-person occupancy. And when you put real homes in there, the spread is quite different. But in perspective to a conventional home, and these open circles are homes that that we also have monitored and studied. These are homes built since the year 2000, so relatively new homes, but with air changes per hour of about 10, somewhere in the range of 6 to 10, so not super sealed with less than 1 air change per hour blower door type level. And so you can see the substantial difference from at 20 degrees, what might be, say, 120 to 180 kilowatt hours per day, down to this range of 20 to 40. And so it's important to keep that in mind. And also, when we get to these high performance, well-sealed homes, we're talking about a total energy of about $3 per day, or maybe about $1 per day per person. So we're really not talking about very expensive energy. This is solar powered energy costs that's based on for running a home. So we want to keep that in mind, that energy is not the standard, even though we're going to show how effective smart ventilation is for being energy efficient. Comment on ASHRAE 62.2, as committee members will agree that it's a ventilation standard. It's not an air quality standard. And the historical background is that it's based on what to me seems unacceptable, that only 20% of the population would be dissatisfied with air ventilated to this standard. It doesn't account for high pollution events. It doesn't account for air distribution. You could just blow air in at the specified level into a closet, and that would be considered okay. And nominally, this will result in about 1,000 ppm of CO2 per person. The table showing what airflows would go with a house of a particular size with so many bedrooms indicates about 30 CFM to about 200 CFM. We're going to look at a couple of examples related to the current US average home being constructed, about 2,700 square feet, with average occupancy of 2.5 occupants. And then we're going to look at a home that's about 1,000 square feet, like the Vermont homes that we've written extensive reports on, with 4 occupants, and just see what the air quality level is and the cost of the energy for managing that level of air quality. As far as ventilation, this slide shows basically how the carbon dioxide concentration for steady occupancy within a room or within a building changes with airflow rate. And as I just mentioned, somewhere around 20 CFM per person, you'll have about 1,000 to 1,100 ppm carbon dioxide concentration. Now this assumes sedentary, and hopefully my monotone voice isn't lowering your metabolism to dangerously low levels. And if it is having that impact on you, you might be with 20 CFM per person at about 500 or 600 parts per million. On the other hand, if you're in an agitated state, if you're physically active, or if you're mentally stressed, your carbon dioxide output can vary by a factor of 8 from your sedentary level. And so the CO2 can easily be well above 2,000 to 3,000 parts per million with that same person, but just at a different activity level. Now, if we improve ventilation rates from 20 to 40 to 50 CFM per person, one study which we have linked, and there's references at the end of this talk, have shown, and this is a large-scale study conducted by Professor Milton, who's now at University of Maryland, but somebody who studies these things in exceptional depth. And he found that doubling ventilation was as effective as the flu vaccine in reducing the transmission of flu. This is, to me, huge, because the cost of doubling ventilation is not that great. And when you think about both the effectiveness of vaccination coupled with increased fresh air, perhaps we can reach even greater levels of avoiding flu as well as colds and other airborne transmissible diseases. The other thing noted on this plot, the ASHRAE ventilation, and again, it's just a ventilation standard that's meant to get some air into a house as we're sealing our homes up better and better. So it's a start, but it does not ensure good air quality. But when you apply that to the occupancy that goes with the assumed range of bedrooms and floor area, you find that at one end of the ASHRAE table, you're maybe less than 10 CFM per person with exceptionally poor air quality. And at the other end, as much as 80 to 90 CFM per person, something that would be energy inefficient to deliver and not much better than a range where we see most of the game. Finally, one more motivating factor. This is just to help put things in perspective on a more global basis. For the US as a whole, just rounding to 100 million residences, and if we reduce from where we are today, maybe about 3 times this amount of energy cost to where we can get with economically optimized, sustainable housing, we would be spending about $160 billion per year for the energy to keep a house comfortable and to allow people to do all the things we'd like to do in our homes. And this breaks down roughly to about 80 billion of it for people activities. That's cooking, TV, hot water, things of that nature. And 80 billion for managing the climate, cooling, dehumidification, and heating throughout most of the US. To put that in perspective, influenza and colds cost us about $130 billion a year. And if fresh air can reduce the transmission of the flu as well as colds, non-influenza viral infections, we could be saving maybe 20 billion a year, maybe 30 billion a year. As far as our energy costs, refrigerators in all our homes cost about 5 billion a year. So we're talking about something much, much greater than the cost of running our refrigerators. Asthma now impacts 8 to 10% of the populace. About 1 out of every 4 homes most likely has somebody with a respiratory sensitivity of some type. And asthma alone costs about 60 billion per year. Just 30, 40 years ago, we were at about 4 to 5% of the populace. The increased incident correlates very strongly with sealing our homes up, but the causation of it is still not readily known. But fresh air seems to be an important ingredient for reversing this trend. And perhaps we can get back to 4%. Perhaps we can cut another $25–30 billion out of medical costs by more effective ventilation in our homes and buildings. And then finally, the big dog. Recent studies are just showing that with current ventilation rates, we may be losing 10% of our cognition capability with a value that's been estimated at about $1.5 trillion a year. Maybe this is off by a factor of 10, so we'd only be talking about 150 billion per year. But again, very cost effectively, we can increase the ventilation rates to improve our decision making, our creativity, our focus, our ability to organize information. I want to just show the difference, and there's tons and tons of data. This is not cherry-picked data. And as I mentioned, you can look through 4 years of online data from my house, which has been ventilated, smart ventilated since 2010 when we built it. But a smart ventilation system, whenever CO2 or VOCs hit the threshold, these green bars show a fresh air period. And at other times, there's still air coming in, even though this house is sealed to 0.6 ACH at 50 pascals. when the wind blows, there's air coming in. When the door is open, there's air coming in. So there's a variety of sources bringing air in. But you can see how as more people are in the house, as there's a cooking event, as there's a cleaning event, automatically it's taken care of. We don't have to think about it. But in a home that's set up with, this is a certified passive house with a very high efficiency HRV, and it's set up to ventilate at ASHRAE ventilation standards. But basically, when people are home, it's polluted. When they're gone, it's not. When they're back, it's polluted again. There's no recirculation in the home. And when you divide the home into several zones, the amount of airflow that's been divided up for the zone where people are typically is not sufficient. So let's look at, this is simulation data, but it's from simulation models we've developed that have been vetted against field data. And the reports that we're releasing over the next couple of weeks, and you'll see some newsletter articles that will announce these reports so that you can look into the nitty-gritty details that form these reports. More information on the 5-minute computer simulation analysis that we've conducted, more information about what makes up the overall energy terms for these different systems. But basically, we're going to focus on data from January 2010, hourly weather data that then have been broken into 5-minute simulation periods. And the 5-minute period is essential in order to not smear over the dynamics of the concentration variations that are occupancy in a home, as well as what the wind impact on infiltration, and then the energy impact of switching systems on and off into different modes will have. We're going to use the SURF2's performance, which is documented, and in the back of these reports, all the information related to how the coefficient of performance of the SURF's heat pump varies with outdoor temperature in heating and cooling, how its dehumidification varies. All of that detail is included in these reports. And we're going to study 2 average homes. It's hard to believe a 2,700 square foot home is average, but that's what the U.S. Census Bureau states is the average home being built now. The International Residential Code states that homes should have infiltration no greater than 3 now. And but many of you involved in home design and construction are hitting passive house levels of 0.6 ACH at 50, like we did in 2010 with our Equinox house. 2.5 occupants is a typical occupancy, and so let's look at average and just see how the energy changes with these 2 types of ventilation. And then just for comparison, home D, let's look at a 1,000 square foot home like a Vermont home. Also very well sealed, but it's a 2-bedroom home, and typically it's not unusual to find 4 occupants in it. So using ASHRAE ventilation standards with that type of home to look at its air quality. Now the January data, this is temperature and wind. It's a lot like the January we're having right now. We had some 0-degree weather. We had some below 0-degree weather. As you look at the orange outdoor temperature variations, hourly variations, it was windy, it wasn't windy. January on average, as you can see, was a pretty windy month with probably an average of about 10 miles per hour. Other times of the year are not so windy. And on average, this month is about 20 degrees. Our typical January average is about 21, 22, so it's not too far from average. But these real variations are extremely important in order to understand how smart ventilation operates and why it's efficient. And before we compare those homes, just one note on a leaky home. Here's a 2,700 square foot home, this so-called average home, but with 10 ACH. Something that was being built around 1980. And today's homes, without much effort, people are typically hitting 6 ACH. And now many of you familiar in the business know hitting less than 3, hitting less than 1 is getting to be more and more typical. But it wasn't that long ago when 10 ACH was common. In this home, so wind speed is plotted again on here. Basically, you can see that when it's windy, there's lots of air whistling through the house, and the carbon dioxide concentration is quite low, about 500 ppm. And when it's not windy, that with 5 occupants in the home, it relative to say 800-900 ppm as a level of air quality that we might like to maintain, it exceeds that, at least 5 days of this time period. And then who knows what the VOCs are, depending on the cooking, whether it's gas cooking or electric cooking. But overall, the energy required, and this is electrical energy, and what's assumed is that a high performance heat pump, an air source heat pump like a hyperheat, is being used to provide the heat to take that infiltrated air from outdoor conditions up to room temperature, that we would use about 2,200 kilowatt hours, or maybe about $250 of the utility bill would be for infiltration heat losses for this month. So a pretty significant part of the energy bill is due to infiltration. But again, it's a myth, and I can't tell you how many times someone has told me I live in a leaky home, I don't have to worry about air quality. Where the leaks are and where you live are typically different. And I can tell you that more than half of the homes, conventional homes that we've monitored, more than half of the time have poor air quality, whether in the bedroom, in the family room, or somewhere else. And we'll see a bit more data in a bit. So this average home A with a 90% efficient HRV, a relatively high quality HRV, on average, it looks like good air quality, about maybe 500 to 600 parts per million throughout the month of January. So the hours on the bottom scale, those are each hour of the month for January. And the carbon dioxide on average for the ASHRAE ventilation rate of about 120 CFM, the house at 3 ACH, so really a quite well-sealed home for today. And then with 2.5 people, and this assumes steady occupancy, we'll look at some results with an occupant schedule, but just to not add in the complexity of people in the home, not in the home, sleeping versus exercising, that we just have them in the home steady for the whole day. But 893 kilowatt hours, so less than half of what the Leaky home had. On average, good air quality, and if there is recirculation, then it should be good throughout this home. Looking at a smart ventilator, the way it would operate in this home, because 3 ACH does bring in significant amount of infiltrated air to the house, a smart ventilator would recognize this, and for those times when it's less than the set point on the smart ventilator, in this case we've assumed 1,000 ppm of CO2, that when the indoor air quality would exceed 1,000 ppm, that then it would kick on and it would operate until the air quality is below 900 ppm. The reason for this selection, even though I've mentioned that we prefer people to keep 800 to 900 ppm as their threshold, is that this is roughly equivalent to where ASHRAE 62.2 ventilation standards would keep the typical home, even though there is a wide variation, as we discussed. And so this is to try to get us to an apples to apples comparison as much as we can. Now, what you'll see is that the energy for this home because it knows when it doesn't need to bring fresh air in, so it can be contributing in recirculation its heat pump comfort conditioning to the home. And then when it does hit this threshold, during those times when the wind was low enough that infiltration wasn't bringing in sufficient air, then it's heating the outside air while recovering energy from inside air that's being exhausted. And this lowers the energy usage of the house by about 250 kilowatt hours. It's about a 30% less energy usage than what an HRV would use. And then to remember that there's significant recirculation. Most of this system's time is not spent ventilating, but it has significant time for recirculation throughout the home. And so that would be expected to be pretty similar through the home. Now, home B, let's seal the home up from 3 ACH to where a number of folks are hitting 0.6 ACH now. Still with ASHRAE ventilation of about 120 CFM. And we see that even though a home with 3 ACH is quite well sealed, this home for this January weather would drop from about 900 kilowatt hours to about 430. It would be less than half of the ventilation load. So very worthwhile to seal this home up to hit this level. And because of the lowered infiltration to the home, where home A with an HRV was at about 500 parts per million, we're now averaging maybe 600-700 parts per million in the home. The same comments as before. While on average it's showing this, as you divide this airflow up, the 119 CFM throughout the home, that it's not sufficient without recirculation for keeping the air healthy in bedrooms and family rooms and other places where you live. Home B with a smart ventilator, there's a lot of detail because of the 5-minute simulation. And so you're kind of seeing what looks like noise around 1,000 ppm. But with steady occupancy in this home with it well sealed, very little of the time is wind infiltration sufficient for keeping the air fresh. But this is actually a desirable effect. It is best to not ventilate your home with infiltration because it's generally coming through paths that you don't know where they've come from. And so to control the air that's coming in is a real benefit. But the 5-minute details of this hitting 1,000 ppm being brought down to 900 ppm and then going back up. If I expanded this out to just a few hour type range, you'd see the dynamics of the 5-minute ventilation and then recirculation. So this home still has a lot of recirculation going on. In fact, it has about 70% of the time it is in recirculation, even though you see it hovering right around the set point. There's a substantial drop in energy for this well-sealed home from the HRV home, about 40% less energy. But that's somewhat magnified. The energy difference is about 160 kilowatt hours, or maybe about $20 per month, but still a benefit. It's better ventilated and it uses less energy. Home D is on the opposite end of the spectrum. 1,000 square foot home, 2 bedrooms, 4 people, 2 children, 2 adults. And again, steady occupancy in the home, which, you know, many homes people are not in the home all the time, but other homes, people do occupy them 24 hours a day. This home with a 90% HRV using the 53 CFM ventilation level that ASHRAE would give you only uses 200 kilowatt hours, maybe $25 a month for ventilation in this very cold month, but the air quality is unacceptable. As you get up around 1,200, 1,300 parts per million, you are being impacted by the air quality. You're going to get sick more often when someone in your home is sick. More than 25% of the general populace would think your house stinks. And with smart ventilation, keeping it pinned at this level, and again, it looks like noise, but there's a lot of detail within this when you look at the 5-minute level. You're going to use more energy in order to keep this home at a better air quality level. It's about 120 kilowatt hours more for that month, which boils down for 4 occupants in it, about 12 cents per person per day for much, much improved air quality. And so smart ventilation may use more energy, but it's doing it because you need more ventilation at certain times. And so that's the main point of that. Let's talk a little bit about distribution. And so on this final thing, a lot of the distribution is common sense, but for some reason, a number of folks have gotten off on a path of thinking that distribution is not important or can be neglected, or that if you just put air into a house, surely it must somehow move around to where you are and meet your needs. Tons of field data we've collected and others have collected have just shown Lawrence Berkeley National Lab data on air quality in homes, Washington State University's excellent study on air distribution in homes. Without recirculation, where you are is going to be polluted, and where you're not is going to have excess fresh air. While some folks like to euphemistically call this cascading ventilation or just constant flow ventilation, we call it one and done ventilation. This simple schematic, the air is polluted where these people are, even though they're being delivered through the house as a whole, the right amount of ventilation. And then as the air is extracted, the air that went in the unoccupied areas, it didn't do you any good. It's a waste of conditioning to bring that in. And so with recirculation, you're going to make use of that stored fresh air and keep it fresher where you're living. You're going to have a chance to filter out particulates, and your comfort is going to improve. Just as far as comfort, if you think of just depositing fresh air in here on a continuous basis, and then it has to work its way over to be exhausted, this doorway or whatever this opening is going to wherever air is exhausted, this is a barrier for if you had, say, a point source mini split over here conditioning it. This conditioned energy from a ductless mini split can't magically get over into this room if air is flowing out of it. With recirculation occurring, you can move some of that comfort over. So here's a constant, here's a simulation of a constant flow ventilation in our 2,700 square foot home, but now with some scheduling brought in. And this is without recirculation. So if this home were well mixed, and basically the schedule, we're assuming that there's 5 occupants in the 4-bedroom home. So it's loaded up to what would be a assumed occupancy level based on the ASHRAE standard. And the 120 CFM ASHRAE flows broken into 60 CFM for the main, 20 for the master, and 10 for the other 3 bedrooms. And if the house were well mixed, we would follow this path of the brown. And on average, the air quality looks pretty good if it was well mixed. But the reality, and the schedule assumed, is that people are sleeping from 10 at night to 6 in the morning. The metabolic activity is reduced when you're sleeping compared to active. And then getting up at 6 in the morning and being quite active until 8, and then leaving the house from 8 until 4, and then returning home and having different levels of activity. say from 4 to 6 and then 6 to 10, that it gets quite complicated. We see in the main room, even with 60 CFM, half of the airflow brought in, that room's going to be quite polluted following the gray scale. In the bedrooms, that generally they look like they may be okay, but they're also starting to get higher. Now, if in balancing these, the main room got more of this air and the bedrooms got less, the situation easily reverses itself. If we have someone that's in one of the bedrooms that's sick, the red line on top, and if they're sick and continuously in that room is going to be have exceptionally poor air quality. And that level of CO2 is directly linked to the probability that somebody is not sick is going to get sick. Here's a home that doesn't have, this is real data collected about a year ago. It's a 3-bedroom home, 2 adults, 3 children. It's 1950s construction. And so while I don't know the blower door infiltration, I can assure you it's probably about 10, maybe a bit less, but certainly greater than 6. So the house as a whole gets a fair amount of infiltration, but where people live and where the infiltration occurs are different things. And in this case, there's not significant recirculation in the winter because it has radiant heating. And so the main thing is that the gray line, which is in the children's bedroom where 2 of the kids sleep, that when they first go to bed around 7 o'clock, the air quality shoots up to a very high carbon dioxide concentration, 1400, 1600. Around 9 o'clock at night, the parents, once the kids are asleep, open the door, and you can see improved ventilation, but still not good air quality. You can see in the main family room and living room, most of their time is spent in the family room rather than the living room, that these also have relatively poor air quality. And so this is a home that for sure, with its occupancy level, could use better fresh air ventilation. And on top of that, needs to have recirculation in order to properly manage the fresh air delivered to the house. I mentioned how probability of getting a cold or getting a flu is related to carbon dioxide level. On this plot, with a carbon dioxide level on the lower axis of 2,000 parts per million, you walk into that room, if you're in there for a few hours, somewhere between, say, 30 and 60% chance that you're going to come down with a cold. A similar plot can be made for the flu virus. Flu is much more infectious than a cold, than rhinovirus, and it can be more in the range of a few minutes rather than a few hours that you're likely to catch the flu, with carbon dioxide concentrations in the range of about 2,000. And basically what carbon dioxide concentration is telling you is what fraction of the air in a room or a space was already breathed by someone else. And of course, that's an indication of airborne contagions. Getting down to 800, 900 parts per million, you significantly reduce the probability that you're going to get sick when someone else in the home or building is sick. So let's talk a little bit about recirculation. Basically, recirculation is a way to move air around the barriers that we build in our homes. So opening up a home is a very good thing because then the volume is pretty well mixed on its own. But as we do partition off bedrooms and other rooms, that recirculating in effect is creating a larger home or a well-mixed home. And it's making use of the air in the unoccupied regions, but in a fairly passive manner. And then, as we mentioned, it is giving you the opportunity to to filter out particulates, which are significant. 90% of the particulates in today's well-sealed homes are indoor generated. They're not passed in from the outside. So a home that's about 2,000 square feet, 8-foot high ceilings, with 200 CFM, the flow level that we run with our serve units under typical conditions, that this would take about 80 minutes to circulate the volume of the home air through the house. And somewhere around, say, less than 2 hours circulation time. In those homes, recirculation is sufficient. Here's some real data from Equinox House with some sensors, air quality sensors placed in the main room, the master bedroom, and then an unoccupied smaller bedroom. Equinox House has 4 bedrooms and it's about a 2,000 square foot ranch. And you can see that we have the set point at 850 parts per million, and the serve, which is seeing mixed air from the house brought to it, that it is somewhat intermediate to these other levels. It's a very dynamic situation over this 5 to 6 day period. You can see that the main room earlier in the day, say before 10 o'clock, is likely to have higher pollutant levels than the master bedroom during the nighttime, as pointed out on the graph. But overall, what you see is that the recirculation effect is keeping all of these within fairly reasonable bounds, that we're not seeing over 1,000 ppm in the bedroom at night, and that air quality, and we're not seeing air within unoccupied areas such as the one bedroom being wasted. When the time constant gets greater than 2 hours and a home gets more complex with more walls and rooms, and so, for example, a 4,000 square foot home with about 200 CFM would be a bit more than, say, 2.5 hours to recirculate that. Then starting to think in terms of zone control. And in zone control, you still want recirculation for the same reasons we've already mentioned. But now you have the ability, and in our case, through an array of wireless sensors, so that when somebody moves into a room, that you can locally sense the air quality, or perhaps it's an occupancy sensor, or perhaps it's a switch that somebody just presses because they feel like they would like to have enhanced airflow in that region, or perhaps it's a circuit sensor that senses that you've turned on a light or you've switched on the kitchen vent hood. But in some manner that then dampers, which may be wired or wirelessly communicating with the ventilation unit, that they should be opened or closed. And just to give you some physical pictures, we have an array of these sensors, and there's more and more types of sensors coming out that we'll be introducing over time. But for example, this battery-free CO2 temperature and humidity sensor, this battery-free wireless switch where your thumb power is the energy, allowing it to chirp a signal to the serve. And then these active circuit transmitters that and relays that are self-powered through the circuits they're attached to. And this is one simple example. I won't go into detail on it, but for example, if somebody wanted enhanced kitchen venting, whether they switch the hood on and a circuit sensor is shown here, detects the hood is on, and so that tells the serve to automatically go into an enhanced ventilation mode. But a damper could squeeze the air off. You don't totally close the air off from other rooms, which then locally enhances the airflow coming from the kitchen area where pollutants are being generated. But it's really up to your imagination and creativity to think about how you may want to place both supply as well as exhaust type dampers for zoning. So it's a new world of capabilities, but then they are very linked together in a very simple manner. As I mentioned, Ben, in February, will give more detailed description in a webinar talking about the serve and its capabilities. To give you an idea where we're going, we don't think of ourselves as a ventilator. We feel we're a piece of the puzzle to help us feel better, to improve our health. And so the serve is one piece of this, and it's a system. Your health and your comfort, something we call preventilation, how we prevent, how we avoid, how we mitigate ill effects that are due to air quality, due to our activity, due to our nutrition, due to the outdoor environmental effects, due to how much the sun shines, due to how much TV we watch, but in some manner, these days of big data and artificial intelligence, in a beneficial manner that these can be used, how we, in a seamless manner, improve our health so that we can live happier, live longer, and enjoy life. So I'll just summarize, and I'll mention that there's a bunch of references here, and those lead to more references and more references, so you can read forever. But the cost of poor air quality, we need to think beyond energy. Your health is more costly. You are more valuable than energy. Don't sacrifice your health for saving energy. Use energy wisely, but your health is important. Smart ventilation helps us, while it is technically complex, when it's managed in the right way, it manages air quality automatically and is extremely energy efficient, and it should give you the peace of mind to remove that stress associated with worrying and wondering whether things are okay in your air. This is just as important as the air quality itself, is that you have a peace of mind that things are being managed. And smart distribution, kind of the forgotten child of ventilation. Recirculation is essential. You need to recirculate air within the home to get rid of particulates. You need to recirculate air to make efficient use of air that's in unoccupied areas. And you need to recirculate air in order to help manage comfort. And when you cannot recirculate at a sufficient level, when the airflows just get too high, and to us something above 200 CFM is starting to get to be a lot in today's high performance homes, then looking more directly at zone control, where those areas that are more polluted get the pollutants out when they're most concentrated. That also adds a level of efficiency to ventilation in the home, and extract it where it's most polluted and supply fresh air where it's most polluted. Thank you very much for attending. I'll take a look and see if there's some questions I can answer. But again, please contact us anytime to answer questions. And let me see if I can